Hello, this is Concrete Path. Today's lecture is about the strain transformation and concept of plane strain transformation. Till now we have studied the stress transformation and the Mohrs cycle related to that. Now we'll be dealing the strain, the stresses, induced strain. So we say that let's have the strain. We say first topic is that plane strain condition. Plane strain condition. That plane strain condition. Till now we studied that plane stress condition. In the plane stress condition we said I want sigma z to be 0, I want tau xz to be 0, and I want tau zy also to be 0. That means I don't want any stress out of the plane xy. So this was our that must goal. This was we had to ensure that this won't be there. This should be 0. This was the must condition. Similarly for the plane strain condition, that we say your strain in z should be 0. The strain in the z direction should be 0, and the shear strain corresponding to plane xz and shear strain corresponding to plane zy is also 0. So we want these three to be 0, and all other three that are strain x, strain y, and gamma xy, they may be 0 or may not be 0. May not be 0. So but the strain in z has to be 0, gamma x has to be 0, and gamma zy has to be 0 for the plane strain condition to develop. Now since from the Poisson ratio we know if the strain z is 0, that means sigma 3 by E minus mu, sigma 2 plus sigma 1, or we can keep it in the z direction. We say sigma z, sigma x, and sigma y by E. So this is our strain z. We say strain z has to be 0. That means either sigma z in the, then this condition has to be satisfied that if the strain in z is 0, that means sigma z equals to mu times sigma x plus sigma y. So this becomes condition. And similarly for the plane strain condition, we say sigma 3 has to be 0, or we can say sigma z has to be 0. Sigma z, stress in z direction is to be 0. That does not mean that strain in z is 0, because we can say 0 by E minus mu sigma x plus sigma y by E. So in the plane stress condition, we say strain is 0 only, strain in z is 0 only. This is normal strain. In z direction is only possible to be 0 if mu is 0, or sigma x is negative times minus time, or we can say minus times sigma y. This is only possible to be 0 in the plane stress condition, when sigma z was 0, but it can have value because of Poisson ratio. But if you want strain in z to be 0, that means mu should be 0, or sigma x equals to minus sigma y. So this was the condition for plane stress condition. Then we say for the plane strain we want strain z to be 0, gamma xz to be 0, and gamma zy to be 0. Now, so this is the difference we can have. We can say that we can calculate that plane strain and plane stress condition, or we can say components. The components we get, they are not same. You can keep y, because you can have example of sigma z. So sigma z is 0 in plane stress condition, but it can develop in the plane strain condition. It can develop in the plane strain condition, or it can be 0, but it has to be, it may not be 0 always. So when you are strain in z, there is chance of that strain would develop, that stress would develop in, let's say this is the sigma, this is direction z. If you are preventing strain in z, I would say some stress would get developed in the sigma z direction. I would say sigma z. there's a chance. Yeah. So now we would say let's transform those equations which we have in the stresses. If we say let's transform those equations of stress transformation, and similarly we can say on those similar grounds, I would say if we transform them, I would say your normal stress changes to normal strain, and your shear stress changes to shearing strain by 2. Your shear stress changes to shear strain by 2. This the reason here for this one. We know that gamma xy is 2 times theta. That was actually theta 1 plus theta 2 when we studied it in the first lecture, that you had shear stress. We know shear stress tau xy equals to tau yx. Actually, the shear stress is acting on some particular plane, let's say this plane P, and tau yx is acting on plane Q. So we said that because of tau yx, that's deforming the material, say in this fashion, and there's some angle and change between the two axes. So this was actually initially the two were at an angle of 90 degrees, but it has deformed by some angle of theta 1. Similarly, because of tau yx, it has deformed in this fashion because of tau yx. So it has deformed in this fashion. So there's some theta 2 developed. So but we say that tau yx equals to tau xy because of complementary shear stresses. So your tau yx contributed theta 1 and tau xy contributed theta 2. But we say that tau xy equals to tau yx. That means theta 1 equals to theta 2. If you want to say overall effect of the shear stresses for this balanced stress element, because this anti-clockwise moment is getting balanced by clockwise moment, so it's balanced. So I would say for the shear stresses here, tau yx equals to tau xy, it deforms by some angle that's somewhat in this fashion. So this is theta 1, this is also theta 2. So we say this 2 theta equals to gamma change in that gamma xy represents the change in angle between the two axes. That gamma xy is equals to shearing strain in xy plane. That's change in angle. We can say change in angle between two axes. So that's why for in the stress strain transformation would be changing the tau xy to gamma xy by 2. So for the equations we have from the analytical method, that we have sigma x, sigma y, and tau xy. Then we said at an angle of theta, we had some equations. So we had some equations: sigma x equals to sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta plus tau xy sine 2 theta. Similarly, we can write now strain in x dash equals to strain x plus strain x, strain x plus strain y, plus strain x minus strain y cos 2 theta plus gamma xy by 2 sine 2 theta. The critical point here is that gamma xy that's divided by 2. In the stress, it was only tau xy sine 2 theta. Here it was gamma xy by 2 sine 2 theta. And similarly, if you write that strain in y, you can get plus minus and minus. Here in terms of plus you would get minus, and here you would get minus. And if you want to say what is the shearing strain on that particular plane, shearing strain xy dash, that would be equals to minus times ex minus ey by 2 cos sine 2 theta plus tau xy. That's also gamma xy by 2 sine 2 theta cos 2 theta. And this particular thing is also 1 by 2. Actually, it should be also 1 by 2. Yeah, this should be also 1 by 2, because you are talking about a particular plane. You are talking, let's say, at an angle of theta. You are talking about this plane. So on this plane, only some shear stress 1 is acting. There are no two shear stresses acting, because it is only a single plane. So on that particular plane, in a plane stress condition, only one shear stress is possible. Only one shear stress is possible. We know that if you have 3D general case, we say on one plane it has it has three stress components. One is stress in X, one is I would say normal stress, that's normal stress, and two are shear stresses. One is associated with XY plane, next one is associated with, let's say, XZ plane. So one plane, let's say X plane. I'm talking about X plane. So your one plane is representing three stresses: normal stress, shear stress, two. But if we talk about plane stress condition, we say strain Z to be 0, sigma that tau x z to be 0 and tau z y to be 0. That means this part we don't care about. So in the plane strain condition, your particular plane represents only one shear stress component. So one shear stress, we know that one shear stress contributes 1 by 2 of that gamma xy, and this gamma xy is contributed by two shear stresses on two different planes. So for the one plane, you have gamma xy by 2, gamma xy dash by 2. This is 1 by 2. This is also 1 by 2 with gamma x y by 2. Similarly, by the stress invariant concept, we had sigma x plus sigma y equals to sigma x dash minus sigma x dash plus sigma y dash. That is sigma 1 plus sigma 2. Similarly, we can write strain in 1 plus strain in 2 equals to ex plus ey equals to ex dash plus ey dash. If you want to go for the 3D case, you can say e1 plus e2 plus e3 equals to ex plus ey plus ez. So you got this one also. And we had tau max radius, and we plot the Mohrs circle here. We plot the Mohrs circle between the shearing strain, but shearing strain is only 1 by 2. So this is gamma xy by 2, and here we plot normal strain, then we get some circle. So radius would be about that tau max, I would say. In the Mohrs circle, we said for the stresses, we had tau max equals to sigma x minus sigma y by 2 whole square plus tau xy whole square. But for the tau max, that is shear stress acting. It's acting on a one plane. So I would say gamma x in plane. It's also called gamma max in plane divided by 2. That's equals to sigma x minus, that's also called as gamma max in plane, that's sigma x minus sigma y by 2. Yeah, strain. So I would write in terms of strain x minus strain y by 2 whole square plus your tau xy whole square. I would write gamma xy by 2 whole square. So this is our tau max, I would say gamma max in plane by 2. So that's also the radius of the Mohrs circle, that's for strains. Now we also say this one conclusion that along the major principal stress line, along the major principal stress line, or I can say axis, line of action, not control, line of action. I would say along the major principal stress line, along the action of that stress, I would say the major principal strain axis is also there. Major principal strain is also there. Major principal strain axis is also there. I would say E1 is also there. At the rate of sigma 1, we also have E1. So sigma 1, E1, they are parallel, I can say. They are parallel. So now we have said, we say that what should be there is some convention that let's say that your because of the shearing strain, the element has deformed. Your element was, let's say this is ABCD. Your element was ABCD. Now it has deformed in this fashion. It has deformed in this fashion. So this is ABCD, and I would say this is theta, this is theta. So you got some value final theta here. Let's say this is theta. I would say theta equals to pi by 2 plus gamma xy. Yeah, minus gamma xy. So your theta here is negative. Yeah, the theta here is less than pi by 2. If the theta here is less than pi by 2, I'd say that your shearing strain is positive. This shearing strain is positive. This is possible only the shape here is possible only if the shear stress was in this fashion. In this fashion. So this is the case for this. And next one is that if the theta developed was greater than pi by 2, let's say initially the theta was 90 between the two axes that were at an angle of 90, but because of that stresses, because of the shear stresses on that stress element, those points A, B, C, D has reached, let's say this is point A and B, and this is C and D. Let's say this is A, B, and this is D, and C is somewhere here. I would say this one. So this is A, B, C, D. And if I calculate, this is theta 1, this is theta 2, and this is final theta. I would say this is theta. Yeah, overall theta is this one. So this is the overall theta. So theta equals to pi by 2 plus gamma xy. So it's greater than pi by 2. That means the shearing strain is negative. Similar to that, tau xy is negative here because it is developed because of the shear stress that was in this fashion. So this is negative shear stress, and similarly, if the theta becomes greater than pi by 2, I would say your shearing strain is negative. And similarly, this is positive, and because of this shearing strain, your gamma xy is also positive because your theta developed is less than 90 degrees. Now we have the Mohrs circle representation of that strain. Let's say we have Mohrs circle for the strain representation. So we had that this is ABCD stress element, and let's say we say that normal strain. If you want to say this is in the y direction, this is in the x direction, I would say strain x can be represented for strain AB and for the strain CD, and strain in y, I would say strain in along BC and strain along AD. And the conclusion for the gamma xy, we know that this was the representation of general gamma xy, that negative positive. If the theta was less than pi by 2, I would say this is positive shearing strain, and if the theta was greater than pi by 2, I would say shearing strain is negative. But for the Mohrs circle, we know that our convention looks like different. So our convention would looks like this one. Let's say this was actual axis angle 90 degrees, but it has deformed in this fashion. So I would say this was your plane along x-axis. This was our plane DC. I would say this is DC. So it was along x-axis. So it was along x-axis. So this was along x-axis, strain x. So I would say for this plane, let's say this plane is Q, plane Q. This is plane Q. On that you have some strain EX. You have some strain EX, and there is some theta developed. With respect to the horizontal, you have a theta that's anti-clockwise. With respect to the horizontal, you have theta, or this is our reference line, initial line. So with respect to that, you have theta anti-clockwise. That's negative. I would say gamma xy is negative for this part. And similarly, for the next part, I would say this one was your D comma A. This was AD, and it has shifted to another location, that A dash D dash. Then we say there is some theta developed with respect to the vertical. It has developed some theta anti-clockwise. That clockwise, I would say theta is positive. So if the final conclusion is that gamma xy is positive if theta is positive, and gamma xy is negative if theta is negative. Negative means theta is positive means clockwise, and negative is anti-clockwise. Keep it for the sign convention for Mohrs circle related to strains. So this is sign convention. So if you want to represent now the Mohrs circle for this state of strain, say this was our state of strain. I would say this was A, this was A, B, C, D, A, B, C, D, and along this one we said this is strain X and this is strain Y. So if we talk about, let's say it was initially in this fashion, I would say this is plane P and this is plane Q, and along this was strain X and along this was strain Y. Then if you want to plot it by Mohrs circle, say for the plane P, let's talk about plane P. So this was our plane P vertical. So this is plane P, this is our plane P. On that you had strain in X. Along the plane P you have strain in X, and your shear strain is, we talk about this part. That's along the x-axis. We talk about that. So this making an angle of theta. That's anti-clockwise. So your theta is negative. We can say gamma xy is negative. So then the coordinates would be ex comma minus gamma xy, and you have to divide by 2 because we are talking about 1 by 2 on a particular plane. There is only 1 by 2 of that gamma shearing strain. So we are plotting shearing strain by 2 and your normal strain. So to plot the point P or plane P, you have a strain Ex comma minus gamma xy by 2. So let's say gamma xy is negative here somewhere. This is minus gamma xy by 2, and you have a strain X. So this is plane P. Or you can say this is length along x-axis. So then we have one more thing is that that now the next plane, or we can say next phase is this part. This part we it's up to you. Let's talk about this one. Let's talk about plane Q. Let's talk about plane Q. Along the plane Q, your stress is acting. Your strain is along in this direction, perpendicular to that. I would say this is strain Y, and if we talk about this one, it's making an angle of, say, actually it's making an angle of theta. That's anti-clockwise. Yeah, this is the same thing. Yeah, we have to focus on this one, where it's happened. This one along the Y. That's along the Y. We have to talk about that one. Along the Y, we have strain in Y, and we have some theta that's clockwise. Theta is clockwise. That's gamma xy by 2 is positive. So the location that EY comma gamma xy by 2, that's both are positive. So gamma xy by 2, and we have EY. So this is next point. Then you join them. Then you join them by straight line, and you can get the radius that center equals to. Firstly, you can get center, that's EX plus EY by 2, and let's say this is some center, that's your center C, and radius you get radius equals to gamma max by 2. Gamma max in plane by 2, that's root of EX minus EY by 2 whole square plus gamma xy by 2 whole square. So let's say that radius equals to this point CP. So I would draw a circle. So I would say this one is strain 1, and this one is strain 2, and this one is gamma max by 2 in plane. So this is gamma max by 2. Similarly, if the deformation was such that the axis, the angle between the axes was changes to 90 plus some theta, 90 plus gamma xy by 2, 90 plus gamma xy. So I would say initially the line was between the two axes, the configuration was 90 degrees, but after the material has deformed, the element has deformed, so they have reached somewhere to these locations. So this is A, B, C, D. Now if you want to say, let's talk about this one, that you have this DC, and you take let's say this is strain along X, and you say clockwise is theta, that is theta is clockwise, that means gamma xy is positive. So you got a point that that one is EX comma gamma xy by 2. Similarly, if you talk about this one, let's say this is along the Y, we say strain in Y, and you have some theta developed here, that's you have to take with respect to the reference line. So you have to take with respect to the reference line, that's anti-clockwise. So theta is negative anti-clockwise. So I would say gamma xy is negative. So the coordinates of this one would be ey comma minus gamma xy by 2. So if you want to plot them, let's say this is Mohrs circle, and center would be somewhere ex plus ey by 2. Let's say this is some center, and after that you have to plot these 2 points because you don't know the value of radius. Yeah, you can get the value of radius also. Let's say this is some radius, and you make a circle. You make a circle. Let's say you make a circle. Actually, the best correct way is that you don't know the value of radius directly. If you don't know the value of radius directly without calculating, you can directly plot you can first plot the 2 planes. You can plot this one and this one first, then you can say what should be the radius value. Either the line will cut the y-axis or not. So this is the next point. Firstly you can plot these 2 points. Let's say ax comma positive gamma xy by 2. So both are positive, I say. So this is ex gamma xy by 2. So this is our point 1. And similarly for the point 2, I would say ey comma minus gamma y by 2. So let's say this is strain y and this is gamma xy by 2 negative. So it would be at angle of 180 from each other. So then you make a circle in this fashion, some sort of circle. Let's make it once more. Let's say this was your strain ex comma gamma xy by 2, and similarly at an angle of 90 degrees, at an angle of 180 degrees. Let's say this is our one more point here. The strain is ey gamma xy minus times gamma xy by 2. So then you make a circle, and you can get strain 2, strain 1, and gamma max by 2. That's radius of the circle. So if in the Mohrs circle, for stresses, you said that radius equals to tau max. That means diameter equals to 2 times tau max. And in the strain Mohrs circle, you said that radius equals to gamma max by 2. That means diameter equals to gamma max. Yeah, if you talk about in terms of Mohrs circle, I would say strain 1 equals to C plus R and strain 2 equals to C minus R. You can see from this circle also that this is strain 1, that is center plus radius R, and this one strain 2, that is center minus radius R, center minus radius R. So you can get strain 2 also. So we calculated that gamma max was equals to gamma max by 2 in plane. We know that the equation was ex minus ey by 2 whole square plus gamma xy by 2 whole square. So it's at an angle of, your shearing strain maximum is at an angle of, it is at an angle of 45 degrees with respect to the major principal strain E1, I would say E1. So on the Mohrs circle, it would be at an angle of 90 degrees with respect to major principal strain. So now let's talk about that analysis of principal strain. Let's write the topic that analysis of principal strain. Principal strain. We have that, what we are talking about plane stress condition. Plane stress condition, that we know that strain in X equals to sigma X by E minus mu sigma Y by E. Similarly, I would write strain in 1, that means major principal strain, that equals to major principal stress by E minus mu minor principal stress by E. Minor principal stress by E. So this is the strain 1. Similarly, you have strain 2, that's minor principal strain, that is sigma 2 minus mu sigma 1 by E. Let's calculate that. Let's calculate that strain 2, strain 1. From this equation, I would write E strain 1 plus mu strain 2. And from this one, get the value of strain 2, stress 2. I would say EE2 plus mu sigma 1. You substitute the value of sigma 2 in this equation, and you write sigma 1 equals to EE1 plus mu sigma 2, EE2 plus mu sigma 1. And you get value EE1 plus mu EE2 plus mu square sigma 1. And similarly, you can write sigma 1 minus mu square equals to E1 plus mu E2. That means stress 1 equals to E1 plus mu E2 divided by 1 minus mu square. So your stress 1, that means you, if you don't want to calculate the stresses, if you directly calculate the strains, normal strains, if you directly calculate the normal strains along the strain principal strain 1 and 2, that means using the strain gauge, if you only use the strain gauges that are used to calculate those strains, if you got the strain is in X and strain is in Y, then you can get and you also know that theta would be somewhere, you would be knowing that how much at an angle of how much we have placed that strain gauge. And if you get the value of strain 1 and strain 2, then you can substitute here, and you know Poisson ratio for the material, and you also know Young's modulus of elasticity for that material, and you can get the stress value on that material without calculating from the universal testing machine or from the calculation. You can directly say from this result, by using the strain values, I can get the value of stress 1. Similarly, you can get stress 2 equals to E strain 2 mu strain 1 minus mu square. Let's say we are talking about plane stress condition. We know that for plane stress condition, sigma z is 0, but strain z can be there because of Poisson ratio, because of Poisson ratio. So we write 0 minus mu sigma 1 plus sigma 2 by E. So if we substitute the value of sigma 1 and sigma 2 here, then we see what's the value of sigma z, strain in z. So that means minus times mu by E, value of sigma 1 plus sigma 2. So that's equals to E1 plus mu E2, 1 minus mu square plus E2 plus mu E1, 1 minus mu square. So let's calculate further. You would get minus mu by 1 minus mu square, and you can get E1, and you can get E1 common, 1 plus mu, and plus E2, 1 plus mu, and you can get E1 plus E2 divided by 1 minus mu into minus mu. That's strain z. Minus mu into strain 1 plus strain 2 divided by 1 minus mu. Let's take one more. Let's take the problem first on the concepts of these plane strains. Let's take the problem 1. So this is problem 1 that says that you had some structural member. This is not a state of stress. Let's say this is some member. And we have applied some stresses of, let's say this is 600 in terms of kg per centimeter square. And similarly, you have some stress of tensile 1200 kg per centimeter square, and you have some shear stress. Shear stress is in this fashion. I would say some shear stress value equals to 400 kg per centimeter square, and your Young's modulus of elasticity equals to 2.1 10 to the power 6 kg per centimeter square, and Poisson ratio 0.28. Then we say that you had this member, and we have inscribed a circle on this element. So let's say we have inscribed, or we can say marked using some marker, or we can inscribe it. So this is some circle of diameter 100 mm. So let's write that inscribed circle, 100 mm phi, 100 mm diameter. So because of this loading now, I would say because of this loading, it would get a kind of deformed in such a way that this was your element, so it gets deformed. Let's say it gets deformed by some some fashion. Say it becomes in terms of some ellipse, and the question mentions that it becomes in terms of ellipse, and you need to get the long and small, I would say major and minor principal strain, major and minor axis of the ellipse. You need to calculate the major and minor axis of the ellipse. Initially it was 100, from both the sides. I would say it was 100, but if you know that what's the direction of that, what is the location of that principal strain 1 and principal strain 2, because principal strain 1 would be maximum, that would try to elongate it more, so it would be E1, and because of E2 it would get some value of compression, so it would get compressed by some amount, so then finally we can get the value of major and minor principal, major and minor these axes of the ellipse. So you need to get the strain in 1 and strain in 2. For that you need to get the location of E1 and E2, E1 and E2. But we had the concept that if you have strain in 1, you need to get the location of strain in 1 location. I would say get the location of stress in 1 and get the location of stress in 2 in order to get the location of strain in 2. So but we know that tan 2 theta p, and from that we can get theta. So let's solve the problem now in that fashion. So if I am able to get strain in 1 based on these results that we got, we have the strain in 1 that equals to this one. Yeah, strain in 1, we have strain in 1 equals to, this is our strain in 1 and strain in 2, and we'll be using those. Before that you have to get stress, major and minor principal stresses. Let's say your sigma 1 and sigma 2. Let's write your sigma 1 comma sigma 2, that is equals to sigma x plus sigma y by 2 plus minus root of sigma x minus sigma y by 2 whole square plus tau xy. Tau is negative, tau xy whole square. So you have stress, major and minor principal stress of 1284.886, and you have one more, that minus 684.885 kg per centimeter square. So you got this part. Now you want to say what is the location of that principal plane. So I would write tan 2 theta p, that equals to 2 tau xy by sigma x minus sigma y. So you got a value of that theta equals to 11.98 with respect to vertical. Let's say this is plane P. So with respect to vertical plane P, from that you had to go anti-clockwise for 11.98 degrees to get the location of principal plane. If you want to cross check on this theta, either major or minor principal stress is acting. We got those two values of stresses. We got the two values of stresses. We want to check which stress is acting at theta equals to 11.98. I would say cross check. I would write at the rate of theta equals to 11.98. I would say sigma x dash equals to sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta p. You have to write here principal plane theta p plus tau xy sine 2 theta p, using the proper signs of those stresses, and you can get the value of sigma x dash, that would be equals to minus times 684. So minus times 684.885. So that means this is minor principal stress. So at an angle of theta p equals 11.98, your minor principal stress is acting. That means on theta p1 equals to 90 plus 11.98, that is 109.8 degrees, your major principal stress is acting. And you got this negative, and if you want to represent it, let's say this was your element, and that means at an angle of 11.98, you have some stress element. On that, you have some compressive stress of 684.885. So, and let's say your circle was in this fashion. This was your element. You had some circle in this fashion. Now you got some angle of 11.98. You got some angle of, let's say this is our reference line. So at an angle of 11.98. So this is some angle of 11.98. Let's say this is some 11.98 degrees. On that, you have some stress, that is compressive stress of 684, that is sigma 2. And similarly, on the other face, you would be having tensile stress of sigma 1, that is 1284.886 tensile. This is compressive. So finally you can say we had circle. Let's say you are having a circle, and let's say this is our reference line. Let's say this is the reference line. So at an angle of 11.98. So this is the direction that along this line you have a tensile stress. So along this line you have a tensile stress. That means along this line it's getting elongated. So you have a tensile stress, and along this perpendicular to that you have some tensile stress. Let's say this is perpendicular to that. You have compressive stress developed. So this is sigma c, I would say sigma 2 compressive, and this is sigma 1 tensile. And because of that, the material would get deformed into a shape, into the shape that's in the form of, in this form. In this fashion. Then I would say that this is our minor principal axis. Let's name it as A, and this is our B. Initially for the circle we have A equals to B. A equals to B equals to 100 mm. Now there is some value of now A dash B dash. So A dash would be equals to 100 plus it has elongated by some length of delta 1. Similarly B dash would be 100 and it has shortened by some amount of delta 2. And delta 2 can be calculated from strain 1 and strain 2. From the strain 1 you can calculate sigma 1 minus mu sigma 2 by E, and this one we can calculate from strain 2 equals to sigma 2 minus mu sigma 1 by E, and you multiply that with the diameter. You know that strain equals to change in length by original length. So initially the length was diameter 100 mm. So you write DE1 DE2 equals to D into D. You have this one. So you get the value of delta 1, that's DE1. So and you also got the stresses, that's sigma 1 and sigma 2. So you substitute the value of sigma 1, that's 1284.886 minus of mu into stress 2 was negative 684.885, and divided by E. The value of E was equals to 2 into 2.1 into 10 to the power 6 kg per centimeter square. Finally you get a strain value of strain 1 equals to 7.0317 10 to the power minus 4. And similarly you can get strain 2 value equals to minus 4.9745 10 to the power minus 4. And once you got the strain 1, strain 2, you can get delta 1, delta 2. So that's 100 mm into strain 1, that is 100 mm into strain 2. Then finally you would say that the value of major axis of the ellipse would be, major axis would be b dash. That's major axis of ellipse. Let's say that b dash equals to 100 plus delta 1, and that comes out to be equals to 100.0703 mm. And similarly, a dash would be equals to 100 minus delta 1, delta 2. That's 99.95 mm. That's it from this problem. Thank you for watching this lecture. Thank you for watching this lecture on that plane strain. See you next time.